Okay, so we are now actually starting with the last chunk of Statistical Methods 1. And this is why I also wanted to not do this session just by video, but do this actually with some people present, because it's kind of a new start, last section of this entire winter term course. The topic, as I call it, is Fundamental Designs, which is supposed to give you an overview about the main designs that are commonly being used using the GLM. It's not exhaustive, so there are many more designs that one can specify using the GLM, and whenever you do a GLM analysis yourself, you will likely specify your own idiosyncratic GLM. So the main idea is that you get some structure about how to think about these designs, and also, of course, review some of the stuff that you've heard previously in undergraduate statistics. There's of course the handout, the carbon copy Xerox machine didn't work this morning, so I didn't bring it. Well, I have to be here on. But it's, of course, it's on Blackboard, and you can now also look on the Blackboard copy. It's updated every week. But you also have the version of the class from last year, of course, online. This will be the whole morning. Good. So let's start with the outline. First I want to tell you what we're going to discuss, and also discuss the data that we are using to exemplify these GLM designs. Then we will talk about a spectrum of designs. And then we are going to talk about some categories of designs. And then hopefully we start with a little bit. So we will talk briefly again about simple linear regression, multiple linear regression, and hopefully then also some t-tests. Good. The aim of this whole fundamental design session is now to consolidate and apply essentially what you have learned. So we've talked at length about the fundamental equation of the GLM, and we've seen two examples always for designs. So do you remember which kind of designs we looked at previously and what it meant to look at a design? Interactive part. This is always what happens when you do interactive parts. That's why I rarely do them. Anyway, so do you remember what kind of designs we looked at previously? So what kind of specific design matrices did we look at? Please.
I'm not sure what you mean by that we had numeric variance.
No, that's not what I mean. So we looked at specific instances of design matrices. So we looked at specific forms of X.
looked at the simple linear regression,
Mm-hmm.
and I don't know which other one.
Okay. The other one that we looked at was actually as sampling from a univariate Gaussian. I think maybe this is what you meant. So when we had the design matrix just being a column of ones. Yeah? So that was the other thing that we looked at. And now we want to look at many more variations of the design matrix and the corresponding beta parameters. So everything else will be the same, but we look at different examples for design matrices. As you remember, whenever you specify a design matrix, then of course the interpretation of the beta parameters changes. So do you remember what the interpretation of the beta parameters was for simple linear regression? Mm-hmm. And for the univariate sampling, what was the interpretation there for the beta parameter? Remember? I mean, remember when we looked at the design matrix and then we computed it, or evaluated the beta estimator for this design matrix with just the column of ones. Do you remember what came out? No. So that was the expectation of this univariate Gaussian random variable. That was the interpretation of the beta parameter. So essentially, we will now, having talked about all the theory involved, so how to estimate parameters, how to then do other kinds of statistics on these parameters, like t-tests by doing ratios between the beta parameter estimates and the variance estimates, or doing f-tests, or doing kind of model comparison. So after covering all this theory, we now want to give some more applied meaning to that, going beyond simple linear regression and sampling from a univariate Gaussian. And to do that, we will actually apply a variety of designs to one data set, which is recorded in the handout as a table. So it's this table, and I will tell you now what is in this table, because you don't obviously have it in front of you. So what we have in this table is a data set. It's of course artificial and made up for the purpose of doing these kind of different designs to a single data set. So it's involves, so it's of course artificial, but in this example it involves a number of participants, namely 32. So there are 32 participants, and they are just labeled according to their number. For each participant, two variables are recorded, namely the age, which for simplicity increases to 46. And what is also recorded for each participant is the alcohol level, or the alcohol, not the alcohol level, but the alcohol units that these people consume every week. So it's measured in some units, which is, the example is, one unit is 7.9 gram of pure alcohol. So these are the independent variables, and the dependent variable is the volume of the dorsolateral prefrontal cortex. So that has some neuroscience interpretation, and these are just real numbers. So I'm copying some here from this table. So of course this example is a little bit artificial. So this is a dependent variable. The main reason why I chose this example is because we are dealing with the identity matrix as our covariance matrix. So that means we need independent experimental units. And this is, so because the noise contributions are independent, this is why I use this between subject design, because for within subject design, you wouldn't assume that the noise between conditions are independent. So this opens the whole realm of repeated measures ANOVA, which is not what we are dealing with, but we are using a between participant design. Then the data that we're trying to explain is, of course, like always, an n-dimensional vector. So what is n here? Yeah, thanks. Because we have 32 participants, and then what we are going to do now is to look at different ways to formulate the design matrix and the beta parameter vector, but we will always apply it to this data set. Yeah? So we can, of course, as you will see, implement different designs for this data set, which of course also then have different interpretations, different meaning, but the data will always be this list of 32 values for the dorsolateral prefrontal cortex volume. Yeah. Of course, one could use a more abstract example than this, but it's sometimes people like when it has some real interpretation. Okay, so that's the data set. Questions about this at this point? No. Good. So then the next thing is kind of a overview of what one could in principle do. So that's what I call spectrum of designs. Because one could, one can, like we will see, one can apply many designs to such a data set, but then it also helps to think of if one can apply many data sets to it, is there some structure in the design space that one can essentially apply to any given data set. And one viewpoint is that, yes, there is a spectrum of designs, namely, on the one hand, having a design that predicts essentially the same thing for every experimental unit, or in this case, every participant. And on the other hand, having something that is completely specific to each experimental unit or participant. So these are kind of the ends of a spectrum. Everything identical versus everything specific, whatever that means, and what it means we will see in a second. So the one where everything is identical we have actually seen before, so that's the case where that we discussed just moments ago, where one just views the entire sample as a sample from one univariate Gaussian distribution. So the fundamental idea is that each data point, so now think always of our data vector here, 32, so these volumes of the DLPFC, that each of the entries of this is distributed according to a Gaussian distribution, of course. And they all identical, meaning that there is a single expectation M, which is because this is about a univariate random variable here, obviously, which is hence a scalar, and the same thing expressed in a different way, and this will be how we'll present all of the designs that we're talking about. The same thing expressed in a different way is, of course, that we say that yi equals m plus epsilon I, where epsilon I is distributed how? If yi is distributed according to this normal distribution with expectation parameter m and covariance or variance parameter sigma square, how is epsilon I distributed? If we write the data, the model here as a sum of the mean and an error term?
Mean should be 0.
Exactly.
Sigma square.
You. Yeah, so these are these two viewpoints on the individual random variables that we're looking at. So that one view is that each data point is the realization of a random variable which has a specific mean and has a specific variance. The other viewpoint is that each data point is the realization of a random variable that is given by a deterministic component and under the addition of some normally distributed Gaussian noise, which is zero-centered. Yeah? So I personally like this a little bit more, so that's the probabilistic view. And this is, I think people call this the structural view, or at least they should call it the structural view, because when they talk about structural equation models, that's what they mean by structural. So for, like I said, for all the designs that we will look at, we will always look at the probabilistic view, the structural view, and then of course the GLM view. So if you would like to now write this, which of course for each random variable representing an individual data point runs from I from 1 to n, how would you specify the design matrix and the beta parameter vector? Well, we already discussed the design matrix actually, so how do you specify the design matrix? So that in the end you get for each entry of the data vector, you get the same expectation parameter. Any suggestions? Yes.
So only one column.
Oh. Okay, yeah. So so you're on the right track. So what you basically said is that you want the same. So you talked about the expectation parameter of the multivariate Gaussian right now. So you said essentially mu being this, right? So how, and this would be the expectation of the multivariate Gaussian from which you sample this 32-dimensional data vector. But to get this, how would you need to specify the design matrix and the parameter? No idea? Well, we've seen this before, but since you're all working on posters and blog posts and presentations, of course it gets lost. So the design matrix is just specified as a column of ones, and the beta parameter is then specified as what? Mu? But why mu? This is also, maybe you can't read this. This is an m, a small m. So would you still say mu after this new information, or? You're confused. It's it's what the experimenter bias. So because you're being watched in your performance, you are confused. So it's an m. So if you right, so what you want is in the design in the GLM formulation, you want to put this probabilistic view of that each entry of a y is distributed according to a univariate Gaussian with the same with the same expectation parameter. You want to implement that in the GLM form, and if you want that, of course, you know that for the GLM we're talking about multivariate Gaussians with the sigma square identity spherical covariance matrix. So now to achieve the same expectation parameter for each entry of the data vector, you need to basically set, as you said, the expectation vector of the multivariate Gaussian for the data to all m's. And of course, if you want to estimate m, because it's a parameter, you need to multiply the design matrix with the parameter. And hence, if you have this design matrix, the parameter needs to be m, so that then if you multiply the two, you get this. And this then, of course, is equivalent to this. Yeah? Questions? Or, I mean, we've discussed that previously. That's not really a surprise. Is anyone confused by this? Who is not confused?
I'm just confused with the notations. Why we didn't write directly mu and we wrote m.
I could call it mu, sorry. I just called it m. Yeah, so the reason why I didn't call it, one could call it mu. I mean, it's just a letter, essentially. I think there might be a reason why I don't call it mu in this case, because we will see many more expectations, and as a general letter I used then mu for the expectation, but now we will see specific kinds, and hence I chose m. So, but these are just variable names, right? So it's not that this is something that has to stay always the same. Yeah. The more important thing is that you get clear, or it's clear in your head that this is the expectation parameter. So this here, the expectation parameter of a univariate Gaussian, and whatever that is called, whether it's called A or M or mu. Yeah. Good. So this is the this is the case where everything is identical. So what this means, again, so in terms of making this transparent for the data set, is that you assume that each of these DLPFC values is the realization of an identical value for m. So for example, I don't know, 170, so that all people in this group have the same expected value for the DLPFC value regardless of their age and regardless of their alcohol level. So that's alcohol, obviously, regardless of the alcohol level, and that all the variation that you see, because obviously here there are different values for the DLPFC volume are due to error fluctuations. Yeah? So in a way, this is not the most interesting model, because you know that there are things varying between participants, but you still make the prediction that they essentially structurally are all the same. So you can, of course, also view this as a null model. Yeah. So you assume that the differences that you know that are expressed between participants in terms of age and in terms of alcohol consumption don't contribute anything. Yeah. Now, the other extreme, and this is why it's called a spectrum of designs, is that you assume that each data point is the realization of a Gaussian random variable which has its own individual expectation and of course variance, again for our I from 1 to n, which then in structural form can of course be written as yi being mi plus epsilon I. Yeah. So the important thing here is to note the importance of the subscripts. So that the fact that here we write mi means that the expectation of this univariate Gaussian random variable is dependent on its index. Yeah. So participant 3 modeled by the random variable y3 has expectation parameter m3. Yeah? And this was not the case here. So here the expectation parameter was always the same. Yeah? And this is basically signaled by means of either using the subscript or not using the subscript. Yeah? So these m's over the yi's are all the same in this case, and here the mi's are all different. So any guesses how you can basically put this into GLM form? This is something new that we haven't seen. So you want to basically implement this assumption so that yi is given by the sum of mi and epsilon I, where epsilon I is distributed normally. You want to implement that in GLM form, which means you need to specify a design matrix in a specific way, and you need to specify a beta parameter vector in a specific way. So how do you have a guess? You can just guess.
I already know that.
You saw it, the solution. Does it make sense to you? Okay, so maybe then explain what you see.
Explain an identical matrix by n times n, and I see a beta parameter matrix from a column matrix m1 to mn, and that once you multiply it, then you would get different.
Exactly. Yeah. So what you are aiming for is if you now again see the way you need to think about this always is that coming from the multivariate Gaussian that represents the GLM as discussed, you want to, here I'm calling this multivariate expectation mu, you want to create a mu that as entries has mi, so it has as entries m1, m2, m3 up to m32 in our case. Oh, now the light goes off. Here. a way to do that is obviously to set X to the identity matrix, so IN, oops, not N, but N, and set the beta parameter vector to exactly these values, M1, M2, M3, and so on to Mn. Yeah, because then if you do the matrix product, the expectation parameter of the multivariate Gaussian will be exactly this. Yeah. So this again applied to the data set that we're looking at would mean that you conceive the DLPFC volume of the first participant as a realization of the participant-specific expectation. So, for example, this participant has an expectation of 174, and then there is some additional noise, which you then would explain as measurement noise, and that's the first participant. And the next participant would have their own expectation parameter, M, I don't know, M2 being 170, and again, this would be noise. So again, in this case, you are not, because these MIs, they are not in any way related to this H and alcohol factors, because if they were, we would have talked about it. And we will talk about it. Again, you're not using kind of the information that you have, but just come up with idiosyncratic expectations for each random variable that models a data point. So essentially, the two extremes that one can consider is, so the way I think about designs, and you should also start thinking about designs, is always in terms of design matrices, because this is what you see in brain imaging data analysis. On the one hand, everything the same, so X just a column of ones, or everything different, as we've just seen the identity matrix. Yeah, just for visualization, the first part. Yeah, because then you have parameters that, as expectations, always reflect the same expectation, or for each individual a different one, which has no structural relationship to anything else. Yeah. And of course, in terms of the variance for the designs, we're always using the spherical assumption. So our variance parameters are always the same. It's always sigma square IN. Yeah. So everything that we will see in terms of designs will happen somewhere in between these extremes. Yeah. So the designs that we will look at, except for the simple for the t-test, will not be as simple as this, or I don't know, simple or as boring as this, but also not as over-parameterized as this, because you somehow want to embed some structure in the parameters, and not with the parameters. With the parameters, you don't want to describe the individual expectation, but you want to have fewer parameters than you have expectations or deterministic proposals for each individual data point. Yeah. So this is where now, when we look at specific designs, you should, basically, think that a specific design is more on the extreme of saying everything is the same, or more on the extreme of saying everything is different, but somewhere in between, that's where it will be. Yeah. Good. Questions about this? So this is the spectrum. So this is the space of designs, the end of the space of designs that we look at. Questions? Are you happy with the equations? Good. Then the last thing in this kind of introduction to fundamental designs is the fact that one can classify design matrices or designs into categories. And you have also seen them previously. So this is also not really something new, but something to remind you of. So a fundamental distinction, and also how we will discuss the designs, is between continuous and categorical. And the prototypical example that we've seen for continuous designs was, of course, simple linear regression, where the important thing was that one column of the design matrix was given to a continuous regressor, if you want to call it like that, or the values of the independent variable. So you had, to make this concrete, you had here a column of ones, but importantly you had here specific values, so continuous real values, essentially. So these kind of columns of a design matrix, which are continuous, are referred to, and that's something to get used to, referred to either as regressors, predictors, sometimes also covariates, all the same thing, all columns of a design matrix. And we will talk briefly actually about these continuous designs, because we've seen them before, and we will see them much more also when we talk about fMRI analysis, which is always just a specific case of multiple linear regression. So we will not actually in this last section of the winter term talk that much about continuous designs. We need to talk more about categorical designs, which are indexed, or which are characterized by the fact that the design matrices are full of what people call dummy variables. Dummy variables, or indicator variables. So what are those? Well, they are just ones and zeros. So a typical categorical design, for example, the ones that we just looked at, the everything the same or everything different would be an example for a categorical design. And another example would be something like this, where you have some ones and then some zeros, but you don't have something that varies continuously. So you don't have something like a regressor.
Is it also sometimes ones and minus ones?
Yeah, that's also falls into that category. But this is this has to do with reparameterizations, and we will focus on the case of ones and zeros, because then the problem always is, if you're thinking about designs, of course, is what is the meaning of the parameter? That's always the problem. And if you if you use these ones and zeros, then it's usually easier to talk about the meaning of the parameter, because you have additive effects. So the categorical things, just as a preview, this will be t-tests and ANOVAs. And the reason why we talk that much about categorical designs is, of course, because you also need to refresh your knowledge about the analysis of variance, so ANOVAs. What might hope, or what will hopefully become clearer when we talk about novas is that these categorical designs, they allow for arbitrary shifts in the expectations, so that you don't have between different conditions, you don't necessarily have always the same unit of difference, but you can have differences that are sometimes high, sometimes low, this is a signifying example for ANOVA. So this is why I never understand why people use ANOVA designs to test for linear effects, because also that doesn't work. But I think this is easier once we really go into ANOVA designs. Yeah? So these are these two categories, and we will start with these. I think in the next hour, and get them out of the way, and then we will actually focus on the categorical designs. There's one mixed version of these, which is actually called the analysis of covariance and COVA. And depending on how much time is left in the course, we also talk about ANCOVA. If we don't have the time left, we will definitely come back to ANCOVA when we talk about psychophysiological interaction analysis of fMRI data, because this is just ANCOVA. Yeah. Good. I think that was what I wanted to say in terms of the general outline of what we are going to do for the rest of the term. And I think then next we can start with actually some more real content. So are there questions left from what we've discussed so far this morning? Nope. No? Good. Then let's have a break until short after 11.